Hello and welcome to this video lesson on equations and calculations, specification reference 3.1.2.5. So our lesson objectives for this video lesson are to be able to calculate the masses, that's usually masses of product, from a balanced equation. And we also want to be able to calculate the volumes of gases from balanced equations, which would involve, first of all, calculating the mass, or the moles at least. So first of all, let's have a look at the mass of the product from a given mass of reactant. There's a process that we can go through. It's the same process for any calculation. So let's go through the process first. And the first step would be, of course, to write out the balanced equation for the reaction. Once we've got the balanced equation, then you're going to work out how many moles of reactant you have. And you're going to use the usual moles equals mass over mR. That would usually be the equation you'd use to work that out. And then after you've got moles, you're going to use the balanced equation again to work out the molar ratio. So for example, you might create 2 moles of product for every 1 mole of reactant. And so in this case, your molar ratio would be 1 to 2. So you're going to work out that molar ratio, and then what that enables you to do is to calculate the mass of the product and use the same equation rearranged. So you're going to have mass equals moles times mR. So that's the general process we're going to go through, converting masses to moles and backwards into masses in grams again. So I think the best thing to do is to look at a few examples. So here we have the first example, and it is we need to find the mass of iron 3 oxide produced when 28.0 grams of iron is burnt in air. Okay, so first of all, we'll remind ourselves of our little process. And that's our process there. So we remember that from the previous slide. So let's look at the question again. Find the mass of iron 3 oxide produced when 28 grams of iron is burnt in air. So air means oxygen in this case. So let's write out a balanced equation, which is step 1. So we're going to make iron 3 oxide. The question tells us that. And later on in the course, you'll work out how to get the symbol, the formula symbol from the words iron 3 oxide. But for now, let me tell you that iron 3 oxide is written like this. So that's what we're making, and we're burning iron in oxygen like that. So first of all, we need to balance it, and on the right, dealing with iron first, we've got 2 iron atoms on the right hand side, so let's put a 2 up here. So iron is now balanced, and we've got 3 oxygen atoms on the right hand side. So in order to balance that, what we're allowed to do with oxygen and any other diatomic molecule is write 1.5 here. So 1.5 times 2 is 3, and so now we're balanced. You could have a multiple of this. You could have 4 Fe plus 3 O2 gives 2 moles of iron 3 oxide, but this is slightly simpler. So let's leave it at that. So there we have step number 1 done. That's our balanced equation. And now we need to work out how many moles of reactant we have. Now, so iron is the reactant, and we've got 28 grams of it. Okay, so moles of iron is what we're after. And you remember the equation is mass over. Now I wrote mR before for a compound, but because iron is an element, we can write AR. Okay, so mass over AR gives us the number of moles, and we're told that we've got 28.0 grams, and the AR of iron you can get from your periodic table, and you will find that that is 55.8. So that leaves, if you punch that into a calculator, that leaves moles of iron as 0.502. So now we've worked out how many moles of reactant we have, and iron is the key reactant. We could work out how many moles of oxygen, but it wouldn't help us get to the answer, so we'll leave that step. Okay, so step number 3 is use the molar ratio. Let me just switch to red for the molar ratio. So use the molar ratio to work out the number of moles of product. So we start with 2 moles of iron, and we get 1 mole of iron 3 oxide. So the molar ratio is 2 to 1. Molar ratio is 2 to 1. So that means, switching back to blue, that means that moles of iron 3 oxide is going to be half of the moles of iron. And so that is 0.502 divided by 2, and that comes out at 0.251 moles of iron 3 oxide. So now we have done step number 3, because we have the number of moles of product, which leaves us just with step 4, calculate the mass of the product. So the mass of the product, which is Fe2O3, the formula for that is a rearrangement of our earlier formula. So that's going to be moles times mR in this case, because we've got a compound. It's a relative molecular mass, or relative formula mass in this case, it's ionic. So moles is what we just worked out, 0.251, and mR, let's just go over here to work out mR of Fe2O3. So iron, we've just said, is 55.8, so that's going to be 2 times 55.8, and oxygen is 16, we have 3 of those, and if we add those 2 together, we get 159.6. So our mR of iron 3 oxide is 159.6, which we can feed back into our equation, and then we just work out the mass by punching it into our calculator, and we get 40.0 grams of iron 3 oxide. Now notice I've given that 3 significant figures. This is 3 significant figures, and the reason I've done 3 significant figures is because that's what we're given in the equation, and so that is the answer. Let's try another slightly different worked example. Okay, in this worked example we have hydrogen gas, which you know exists as diatomic molecules, H2 gas, and it reacts with nitrogen gas, also exists as diatomic molecules, nitrogen gas, to give ammonia, NH3, and we're going to have to calculate the mass of hydrogen needed to produce 2.8 grams of ammonia. Okay, so firstly let's put down our process. There we have our 4-step process, and the first one of course is writing out the balanced equation. So writing up the balanced equation, we're going to start off with our hydrogen. Alright, and we're going to react that with nitrogen. I'm spacing it out because I might need to put some numbers in here to balance it. And we're going to get some ammonia, NH3, which is also gas at the temperature of the, if hydrogen and nitrogen are gas, then ammonia is going to be gas as well. Okay, so we want to balance this equation, so let's look at nitrogen first, shall we? We've got 2 nitrogen atoms on the left hand side, and so we want 2 nitrogen atoms on the right hand side. So now nitrogen's balanced, But now on the right hand side we have 6 hydrogens, and so we would need 3 hydrogen molecules on the left hand side. So that is now balanced. So that's step number 1 done. Step number 2, work out how many moles of reactant you have. Well, of course our process assumed we were given the mass of reactant. That's right. So here we're just going to change this into product, because that's the grams we've been given in the question. Okay, so our process is slightly different in this case. So moles of ammonia is going to be mass over MR, relative molecular mass of ammonia. Okay, mass we're given in the question as 6.8, and MR of ammonia, let's just change colour and do that over in the corner here. So NH3, nitrogen is 14, hydrogen is 1 each. Add these two together, you get 17. Okay, so we're going to switch back to blue and then divide the 6.8 by the 17, and that's going to work out at 0.4 moles of ammonia. So now we have done step 2. Okay, so now we want to have a look at the molar ratio. So molar ratio looks, and we're calculating hydrogen, so let's look at the molar ratio between hydrogen and ammonia. Okay, so we've got 2 moles of ammonia made from 3 moles of hydrogen. So you need more hydrogen to make a smaller amount of ammonia. So the ratio, let's say if we write out the ratio NH3 to hydrogen, that's going to be 2 to 3. That's our molar ratio. So what we can do with that is we can work out the moles of hydrogen. So our moles of hydrogen is going to be 3/2 times moles of ammonia. And moles of ammonia was 0.4, so 3/2 times 0.4 is 0.6. So now we've worked out the moles of hydrogen, we can work out, that's done step 3, we can go on to step 4, calculate the mass of the product, and in this case of course it's the mass of the reactant we're working out. So mass of hydrogen, which is what we've been asked for in the question, the mass of the hydrogen, it's going to use our regular equation, which is moles, and it's an element, so we're going to go AR. Well, actually it's a diatomic molecule, isn't it? So let's stick with MR. In any case, we've got 0.6 moles of it, and the MR of hydrogen gas is 2. So we've got 1.2 grams of hydrogen, which is what we've been asked for in the question, and that's the answer. Okay, our first 2 examples involved masses, but in this case we want to calculate the volume of a gas. Okay, so as you can see in the question, we've got what volume of a hydrogen gas in meters cubed is produced when 15 grams of sodium is reacted with excess water at a temperature of 25 and a pressure of 100 kilopascals, and it gives us a gas constant there. And it's interesting to work out volumes, because you need to know what size of apparatus you might need if you were doing this commercially. And so you would work through a calculation that's actually very similar to the previous 2 calculations we've done, except the 4th step is a touch different. Right? So when we get to the 4th step, we're going to calculate the volume instead of the mass, that's all. But otherwise we're going to use the same 4 steps, and of course we'll use the ideal gas equation to work out the volume. Okay, so first of all, we still need to write down the balanced equation. And we've got hydrogen reacting with sodium in excess of water. So the hydrogen is produced rather when sodium reacts with water. Okay, so let's start off with our sodium. All right, we've got sodium solid and we've got water liquid, and that's going to make sodium hydroxide, of course, which is a solution, and as the question implies, we've got some hydrogen gas being given off, which you will have seen in class. Okay, let's just balance this. So you can see on the looking at hydrogen, I look at this and the first thing that pops out is the hydrogens are not balanced because we've got 3 on the right hand side and only 2 on the left hand side. So what we're going to do, because we can't use half numbers with a water molecule, you can't split an oxygen atom, so we'll put a 2 here, and now we've got 4 on the right and only 3 on the left, so we're going to put a 2 here, and now we've got 4 on the left and 4 on the right, dealing with hydrogen. Okay, but of course what we've gone and done is we've gone and unbalanced our sodiums. We've now got 2 sodiums on our right hand side, so let's put a 2 in front of the sodium here, and let's just also check that our oxygens are balanced. We've got 2 on the left and 2 on the right. So we're all balanced. So there's our balanced equation. We've written that down. Let's give ourselves a little tick for writing out that. And work out how many moles of a reactant you have. So our reactant is sodium. So our moles of sodium. And we're going to trot out our usual equation. It's the mass of sodium divided by, in this case, it's going to be the AR of sodium, the relative atomic mass of sodium, and in the question we're given here the mass of sodium, so we'll write in 15.0, and the AR of sodium you're going to get from your periodic table. You'll find that that's 23.0. Feed that into your calculators and you get 0.652 moles of sodium. So now we've worked out step number 2, we've got the moles of sodium. We want to refer back to the molar ratio now. So you can see that we've got 2 moles of sodium to make 1 mole of hydrogen gas. So that means, switching back to blue, that means that 0.652 moles of sodium is going to make 0.326 moles of hydrogen. Let's write out that in long term. So we want to, what we're doing is we're working out the moles of hydrogen gas, and because our molar ratio, I'll write it out completely for us. So we've got sodium to hydrogen gas. Notice I'm putting the 2 there. Our molar ratio is 2 to 1. So our moles, switching back to blue, our moles of hydrogen is necessarily 1/2 times our moles of sodium. So that's 0.652 divided by 2, and that gives us 0.326 moles of hydrogen. So now we've done step 3, and now we want to calculate the volume of this hydrogen, and for that we're going to use the ideal gas equation. Volume of hydrogen is what the question's asked for. What I normally do is I start off with the standard form and rearrange it. So on the right hand side up here I'm just going to write PV equals nRT. So that's the ideal gas equation that I remember. So I can quickly rearrange that so I don't have to remember all the different versions of it. So volume is going to be nRT divided by P. Okay, so let's switch back to blue and write that in. Volume of hydrogen is going to be nRT over P. And now we're just going to substitute in our numbers. So N is what we just worked out, 0.326. That's the number of moles of hydrogen gas. And R is given in the question, 8.31. Our temperature has got to be in Kelvin. Okay, so let's just take this 25, and you remember we add 273 to it to get Kelvin. Okay, so that's going to be 298 Kelvin. Okay, so we'll put our 298 in there. And you remember that our 100 kilopascals needs to be converted into pascals. All right, so it's just 100,000 pascals. So we divide, as a comma there, we divide by 100,000 pascals. And then you feed that into your calculator, and you're going to come out with 0.00247. And the standard units for volume in the ideal gas equation are meters cubed. That's what it's giving us. And if we wanted to write that in decimeters cubed, we would multiply that by 1,000, so that would be 2.47 decimeters cubed. And we've given that to 3 significant figures. 3 significant figures, because our data in the question is to 3 significant figures. And there's our answer. Hope that was clear. Should we have a look at another one now? Sorry, before I do, let me just correct this maths. So we're correct up to here, but this is wrong. These numbers are wrong. So something went wrong in my calculator. This instead is 0.00808 meters cubed. And in fact, we won't bother converting it into decimeters cubed because we are asked for it in meters cubed in the question. So 0.00808 meters cubed is our answer. Thank you very much. We'll try another one now. So let's read the example carefully. The question is asking us for the volume of carbon dioxide in decimeters cubed, and what volume is produced when 10 grams of calcium carbonate reacts with excess hydrochloric acid at a temperature of 25, pressure of 100 kilopascals. Okay, so that's the question, and first thing that pops out is we're asked for the volume in decimeters cubed when we're clearly going to have to use the ideal gas equation. Whenever they give you the gas constant, you know it's the ideal gas equation you're going to be using. And you'll know that the ideal gas equation uses meters cubed. So at the end we're going to have to translate the meters cubed volume into decimeters cubed. Okay, so let's go through our steps. Let's remind ourselves what they are first. There's our 4 steps, and we're going to just adjust this because we're going to calculate volume of product and not gas. But then going through the steps, first step, balanced equation. So let's have a look. The volume of carbon dioxide is produced, so that's a product. So let's write carbon dioxide on the right hand side because that's a product. Let's put an arrow in here just to make sure we know what right hand side is. And then we're told that 10 grams of calcium carbonate, so calcium carbonate, you'll know is got a formula like that, and it's reacting with excess hydrochloric acid. Okay, so when we look at that, what we quickly see is that we've got no calcium on the right hand side, so we're going to have to adjust that. So that's going to be calcium chloride, because it takes the chlorine, and chlorine is in group 7, wants 1 electron. Calcium's got 2 to give away, so the formula is going to be calcium chloride like that. And also, when you're reacting a carbonate with an acid, you're going to get some water as well, aren't you? So let's just check we're all balanced. Our chlorines are not balanced, and our hydrogens are not balanced. We've got 2 of each on the right hand side and 1 of each on the left hand side. So we'll pop a 2 here. And now, just pause the video if you like, but now I can see that that's all balanced. So we have step number 1 done. And step number 2, work out how many moles of the reactor we have. So our reactant is calcium carbonate, and we have 10 grams of it. Okay, so moles of calcium carbonate, using the same old equation, is the mass of it divided by, and it's an ionic compound, so we put the relative formula mass down. Mass were given in the question, 10.0 grams. So put that G in there. And the MR of calcium carbonate. So let me just switch to green and we'll work out calcium carbonate MR. So calcium, you'll see from your periodic table, is 40.1. Carbon is 12.0. Oxygen, we've got 3 times 16. So if we add all those 3 together, then that comes to 100.1. So the MR of calcium carbonate is 100.1. So we're going to divide that by 100.1. And so punch that into your calculator and you're going to get 0.0999 moles of calcium carbonate. Step 2 done. Step 3 is use the molar ratio from the balanced equation to work out the number of moles of product. Okay, so we're being asked for the number of moles of carbon dioxide, and you can see that there's the unwritten 1 in there for calcium, for carbon dioxide, and we're going to compare that to the number of moles of calcium carbonate, and there's the unwritten 1 there as well. So our molar ratio is 1:1, which means that for every 1 mole of calcium carbonate, we're going to produce 1 mole of carbon dioxide. So the moles of carbon dioxide, which is the product we're concerned with, the moles of carbon dioxide equals the moles of calcium carbonate, oops, and so moles of carbon dioxide is also 0.0999. So that is step number 3 done. So now what we want to do is we want to calculate the volume of the product, and why don't I switch colour again, choose purple this time. So I just remind you of the ideal gas equation, PV equals nRT, and rearrange that. Volume equals nRT over P. Okay, so that's the version we're going to use. Switching back to blue, we can now write down volume of our product, right? And the product in this case is CO2, of course. The volume of CO2 is going to be number of moles of CO2, RT, divided by the pressure. Number of moles we've worked out as 0.0999. R we're given in the question as 8.31. 8.31. Temperature, let's check. Now remember Kelvin, So let's just switch to red and do this conversion again. So that's plus 273 gives us 298 Kelvin. Okay, so we're going to write 298 Kelvin in our ideal gas equation rearrangement, and our pressure, going through this process again, our pressure needs to be in pascals. So 100,000 kilopascals, sorry, 100 kilopascals is 100,000 pascals. So we're going to divide this by 100,000. Okay, the rest is easy, as they say. Just plug that in, and we get 0.00247 meters cubed. Okay, now you may remember the relationship between meters cubed and decimeters cubed. What we do is we're going to times by 1,000. Right, because obviously a decimeter cubed is 1,000 times smaller than a meters cubed. Right, so for every 1 meters cubed, there's 1,000 decimeters cubed. So if we times that by 1,000, we get 2.47 decimeters cubed. And we give decimeters cubed because that's what it asked for in the question, and there might be a mark for that right at the end. And that would be the answer, 2.47 decimeters cubed. Hope that's been clear. Okay, so let's finish off by checking our learning objectives. Are we now able to calculate masses from balanced equations? Well, we've had 2 goes at calculating masses. So let's give ourselves a tick. And are we now able to calculate volumes of gases from balanced equations? Well, we've had a couple of goes at that as well. So hopefully the answer is yes. If not, watch the video again. In any case, I'll see you in the next video lesson.